So we looked at Green's theorem in circulation form, and as you'll recall, I'll write it out here. It was telling us that you could trade a line integral at the boundary for a double integral over the region if you use the 2D curl. Okay, and something to note here is that this R is flat and in R2. Okay, it's in the plane. Well, how do we generalize this? Okay, how do we go to an even higher dimension? Okay, take a look at this surface. Now, the surface is two-dimensional object. Okay, it's what's called a 2D manifold, and this one doesn't live in the plane. It lives in space. It lives in R3 because it's curved. Okay, it's not flat. It lives in space and it's curved. All right. So what could we do here for trading a certain derivative in the bulk on this surface for an operation at the boundary? Well, before we get into that, a quick note on what counts as up and down on a surface for a normal vector. We use the right-hand rule. So here's a curve C, and it's running this way, okay? You can think about it as counterclockwise, but again, we're in 3 dimensions now, so those sort of notions are sort of ambiguous. So it's running around this way, and if you curl your right fingers along C, your thumb will point up, okay? And that's where these normal vectors will come in. This diagram here shows you a good way of thinking about that. So notice that your right hand, and you got to use your right hand, okay? Your left hand will give you the opposite orientation. And you curl your fingers along the curve C, and your thumb points in the positive normal direction, okay? So the counterclockwise curve C here would correspond to the normal, the positive normal direction that points above that surface S. There's always 2 vectors normal to a surface, and so you want to choose which one is the positive direction, and this is how you do it. So let's take a look then at Stoke's theorem. Okay. So if S is an oriented surface, meaning it could, you could choose the positive direction, and it lives in R3 with a piecewise smooth closed boundary C, whose orientation is consistent with F in the sense of the right-hand rule that we just saw. And you have this vector field F, okay, and now this is a vector field that lives in R3, okay, then you could trade a line integral at the boundary of S, so C is at the boundary of S, right? So the boundary of S is equal to C. For this surface integral, okay? So we can't call this a double integral because we're not in the R2 plane. This is not a flat plane. This is a flux integral or a surface integral of a vector field. Which vector field? The curl. You'll recall that the curl of a vector field is also a vector field. And so that's the statement of Stoke's theorem and the sort of generalization of Green's theorem in higher dimensions, okay? And yet again, we're getting the sort of statement that tells you could trade some derivative in the bulk being this red surface there, for an operation at the boundary. In the case of Stoke's theorem, the operation in the boundary is the circulation or the vector line integral around C, consistent with the direction of the normal vector and the curve, the orientation of C. Okay, so let's take a look at an example and confirm Stoke's theorem. Before jumping into an example, we could sort of pictorially summarize Stoke's theorem as you see here. This black curve C, okay, you could either do a line integral in the way that we know, okay, or you could trade that for a vector surface integral, a surface integral of a vector field, of which vector field? The curl of f. Okay, not f, but the curl of f. Okay, and the curl of f is in general different than f. Okay, so here this n, the brown vector, is a normal vector, and the curl of f is that turquoise, and f is the red one. Okay, so it's the red vector that you might see there. Okay, don't confuse the curl of f with f. Okay, so the statement of Stokes' theorem is, hey, you could do this double integral of the not the double integral, but the vector surface integral of the blue vector field, okay, over that surface, or you could trade it for a line integral of f over the curve f, not the curl, but f. Okay, so curl on the surface, just the vector field on the boundary. So let's take a look then at example of Stokes' theorem. We're going to confirm it. So let's confirm that Stokes' theorem holds for the vector field. Here's our vector field, and S is the hemisphere, whereas Z, so it's the upper hemisphere of a sphere of radius 2 in R3. Okay, that's the surface, and the vector field is here. Okay, so the boundary of that surface will be the circle, x squared plus y squared 4, and oriented counterclockwise. All right. So that just looks like a very simple top of a sphere with the curve C being the circle, of course, because the sphere intersects the xy plane at a circle of radius 2, just like the whole sphere has radius 2. Okay. So line integrals, we know how to do line integrals. Ingredient 1 is to parameterize C, which is the boundary. Okay. So C is the boundary of the hemisphere. Parameterize it. It doesn't have a z component because we're just in the xy plane, but it's important to write 0 because we are parameterizing a curve in R3, even if one of the components is 0. Okay. Ingredient 2 is to plug in the parameterization into your vector field. So you'll plug it in here. Now we just change z minus y, for example, to zt minus yt, where zt is the z component of the parameterization, and y is the y component. And if you do that, you get that expression here after you plug in your parameterization. Ingredient 3 is to compute dr, and dr is just equal to r prime dt, so the velocity times dt if you want to think about it that way. So we take the derivative, and here's the derivative, and we should also have a little dt right there. Okay. And we use the formula for a line integral. The formula is that it's f with the parameterization dotted with r prime. And you could compute these steps and you get 8 pi. Simple enough. Now let's see if we could trade the vector line integral at the boundary for the vector surface integral in the bulk, right? And on the actual top of the hemisphere. So ingredient 0 here for this problem, I call it ingredient 0 because actually when you do surface integrals of vector fields, you start with parameterizing the surface. Well, I don't want you to forget that you have to take the curl first, okay, when you use Stokes' theorem. So this is our derivative in the bulk, in air quotes there. So you take the curl of f, okay, and if you do that, you get 0, 2, 2. And it's a nice simple vector field there. That's a constant vector field. It didn't have to be that way. And then you carry on with the formal steps of computing a surface integral of a vector field. You parameterize the surface. Here we have a hemisphere of radius 2, and we could use the parameterization borrowing some intuition from the spherical coordinates. Ingredient 2 is plugging in the parameterization into the vector field. Which vector field? The curl, right, of f. And when you do that, well, this is constant. It doesn't depend on x, y, and z, although it could have. And so the plugging in the parameterization is trivial here, okay, since it's constant for any point. So we get that as ingredient 2. Ingredient 3 is to compute the surface area element, okay, ds, the vector. And there you get that by taking the getting the tangent vectors by computing the derivatives with respect to u and v of the parameterization. Then you cross them, okay? This gives you a normal vector. And then you have to decide what if you're going to take the plus or minus. And we went counterclockwise, okay, on this circle. And so we have to choose the outward direction to be consistent with the right-hand rule for what positive is. And so we have this plus direction because that's the direction that would point outward, okay? And there goes our ds vector. And then we just plug it into the formula there. Here is the vector field with, this is not multiplication, okay? This is the vector field curl of f with the parameterization plugged in. And this was simple 0, 2, 2. And here is ds. There it is. You dot these together and then you compute, okay, the double integral. And now you should be pros at computing the double integral. Here we could do some half angle trigonometric identities and we get 8 pi. And so we just confirmed Stoke's theorem in this example. And which one would you have preferred to compute? Okay, on some problems you may prefer to do the line integral at the boundary. So on a curve, okay? In other problems, taking the curl of your vector field will turn it into a constant vector field, and it will be sort of easy to compute the vector surface integral. Okay, so it just sort of depends on the problem which way you want to go. But at least you know, thanks to Stoke's theorem, that you could trade one for the other. And we just saw yet another example of a way that you could trade a derivative operation in the bulk for an operation at the boundary. And here is the pictorial summary of what the example that we just did. You could see that we, on the one hand, computed this vector line integral of the vector field f along this curve C, okay? That was one integral we did. And then we also showed that we get the same answer if we compute the surface integral of the vector field, the curl, okay? So that's the in turquoise there is the curl of f, which is very different than f, right? Here's f. Here's how f would look, and that's how the curl of f would look. So you could trade the surface vector integral of the curl for the vector line integral at the boundary, one or the other, and we got the same answer either way.